All right, so today the goal is to be able to approximate the population mean and the standard deviation using our real-world penny activity. So as you can see on the board,
Whoa, it's upside down. There we go.
there you go. Look, hey, you're in it, Cody. So you can see that the sampling distribution. Okay, I've never done this part before. As the sample size increases, the sampling distribution of all the sample means gets narrower. So the standard error gets smaller. The amount of error gets smaller. So that's kind of what you guys actually demonstrated from your penny activity. So for our notes, the sampling distribution of the sample mean. It sounds fancier than it really is. It's just the distribution, like a frequency distribution, and all of the dots represent a sample mean, right? You calculated all of those sample means from different samples of pennies that you collected within your team. So, for a variable x in a given sample size, the distribution of the variable x bar is called the sampling distribution of the sample mean. That is, all possible observation of the statistic for samples of a given size. So the sampling distributions that we have on the board do not represent all possible sample means, right? Because that would mean that we found all possible samples of size 5 amidst all those pennies, which we didn't, but that would take forever. But the larger that sample size gets, you can see the closer we can get to the actual population mean, and this is a process we use to estimate that population mean. So if I kind of find the middle of kind of all the dots, you can see 1990 starts to become where everything is centered around. And so we could estimate that to be our population mean. Because I don't know the population mean for all of my pennies. That would take forever. Similarly, here in the example, same example as you did in your 7172 notes on your flex day yesterday, we had these 5 basketball players with 5 different heights. This is a really small population. Like realistically, very rarely do we have a population that small, but it's small for the fact that we can find complete distributions. So I can find pretty easily every sample of size 2 given a population of size 5. So there's only 10 dots on here. There they are. Of size 2. Sample size 1, that if I were just pulling out a random basketball player and looking at his height, there would only be 5 dots on there because I'm not putting it back in the box. I'm pulling it out, putting it aside, so I have 5 dots. The mean of a basketball player of height 76 would just be 76. It's weird to think of a mean of just one data point, but you did that on your Math Excel assignment. Hopefully that's familiar. Sample size 2, so that's if I took 76 and 78, added them up, and divided by 2, you get 77, and that's where that dot comes from. And then every other sample of size 2, finding the sample mean. And then samples of size 3, samples of size 4, and samples of size 5. Samples of size 5, there's only one of them, and that equals the population mean, since every element of the population is included in calculating that mean. And same idea, as your sample size gets larger, they get closer and closer to the actual population mean. And that's what this says right here, sample size and sampling error. The larger the sample size, the smaller the sampling error. So for when we're estimating a population mean, by a sample mean X bar. You leave. Take it away. You lost your privilege. You can't interrupt. You can't.
I'll wait until she stops talking.
Finding sampling distributions for larger populations. So when there is a larger population, we can still do a similar procedure as long as the sampling distribution for the variable X bar is approximately normally distributed. Okay, so here's a key fact to know: the mean of the sample mean. So you got all these sample means. Every dot up there represents a sample mean. If I find the mean of all the sample means, I get the population mean. They're equal. That's what this says right here. Key fact. It will be applied several times in your assignment tonight. The standard deviation of the sample mean, however, depends on the sample size, right? That's the sampling error. How spread out the points are depends on the size of the sample, which is why sigma sub X bar is equal to sigma, or the standard deviation, divided by the square root of n, or the sample size. So here's an example. The intelligence quotients. So the intelligence quotients measured on the Stanford revision of the Binet-Simon intelligence scale are normally distributed with mean 100 and standard deviation 16. For sample size 4, use a simulation to make plausible the fact that X bar is normally distributed. We need to know that fact that X bar is normally distributed in order to apply these principles. Here, the simulation was done for us using a computer. It generates all these different values within a certain range, depending on how many samples that you ask it to find. So the computer generated 1,000 samples of size 4 and dropped them into a frequency distribution. And the frequency distribution, that's a lot of samples, 1,000, was normally distributed. Therefore, we can assume that the data set for X bar is normally distributed. So we can apply the above. So for a sample of size 4, let's obtain the sampling distribution of the sample mean. We already know that mu sub X bar equals 100, since it says the mean of the population is 100. But sigma sub X bar, we need to calculate by taking the sigma and dividing it by the square root of n. It says the sigma, the standard deviation, is 16. And in this question, the sample size is 4. Square root of 4 is 2. So that means our sigma sub X bar is 8. And so it's actually standard to write that out with the mean first, followed by the standard deviation. And those values are represented in this distribution right here. I'm not making you draw it because I think it's important that they're drawn correctly. And you can see as the standard deviation gets smaller, the curve goes higher and is more narrow. So then, again, for a sample of size 16, we plug in n equals, that's our n value. The mean sub X bar, the mean of the sample means remains the same, 100. But the sigma sub X bar is changing. Well, it should shrink because the sample size increases. So our standard deviation is 16 and our sample size is 16. So that's going to be 16. Square root of 16 is 4. So 16 divided by 4 is 4. And that one's displayed right here. And again, the curve gets narrower and higher. And that's important to notice because the area under the curve is always the same. Who remembers what that is? What's the area under a normal curve? 1. Good. The area under the curve is always 1. So if it does become more narrow, it should become higher because it should have that same area underneath. So all of this leads us to the foundational theorem of statistics, the central limit theorem, which says for a relatively large sample size is a size 30 or more, it says down here. The variable x bar is approximately normally distributed, regardless of the distribution of the variable under consideration. So the approximation becomes better with increasing sample size, just like we talked about on the front. That's a pretty impressive thing to say, the central limit theorem. Again, it says, if your sample size is large enough, your distribution of all of your x bars will be normal. It's crazy. So that's the central limit theorem, and that will be applied further as we go on in the course. And that is your notes for 7.3.